So I'm just going to ask you, can you all hear me okay? So bash something into the chat if you can hear me okay. Yes, I have from Jane, yes. Igor, yes. Fantastic. Okay, that's great. 100 people are writing to me to say yes, they can hear me. This is grand. Okay, thank you very much. So the first thing you need to know is this is being recorded, but I don't think any video or any audio of the attendees is going to be included in the webinar. So your image and your voice won't be captured, but it is being recorded and we will post it and let you know where it's posted so that you'll be able to watch this back in the future if you ever feel so moved. Good morning if you are anywhere near me. Good afternoon or good evening if you're far away from me, wherever you are in the world. I think it's amazing that we're using internet technology to be able to have a massive online lesson like this, especially with what's happening at the moment. I think the internet is really coming into its own. So today, we're going to spend an hour looking at something called Pell equations. Okay. And Pell equations are a type of equation that can turn up in lots of different problems, sometimes quite surprisingly. You come across a Pell equation and you think, my goodness, how do I solve this equation? It looks really simple. There are only two variables and I just need to find integers which solve this type of equation. And it's quite frustrating if you're not sure how. So we're going to focus on how to solve Pell equations. Pell is the surname of a mathematician, and when I was researching a little bit about him, I believe it turns out that Pell isn't really responsible for working out how to solve his own equations, which is interesting. That happens quite a lot in mathematics. Something gets named after somebody, but it doesn't really belong to them. They didn't invent it or solve it. So you can Google Pell and find out a bit more about him. Before we begin, we're going to have to work out some vocabulary. So I need to just make sure that you guys are able to understand some words because you're from all around the world. And I need to make sure that you are able to understand some of the notation that we're going to use. So first bit of vocabulary, natural number. In English, natural number just means any number in the list 1, 2, 3, 4, and so on. So these are the numbers we use to count. And the symbol that we use for these numbers in mathematics is an N, like this. And that N stands for natural. And we just give it a sort of fat trink in the middle. Okay. Next word that we need is integer. And the integer is all of the natural numbers, including the negatives of all the natural numbers, and then including 0 as well. And the letter that we use, the symbol we use for those is a Z, like this. And that Z comes from the German word Zahlen, which is German for number. So that's why we use a Z. The next word is the word equation, which is an expression with an equals sign. And the equa in equation comes from the Latin root for the same. So an equation has an equals sign. And this symbol here is the equals sign. And the reason we use that for equals is because it's two lines of the same length. So those lines are the same as each other. Okay. A solution is any number which satisfies an equation. So for the equation above, 2x equals 6, x equals 3 is a solution because if we substitute x for 3, we get 2 times 3 equals 6, and that is true. So 3 is a solution to the equation 2x equals 6. And finally, we need to know what the square root of a number means. So when I say the square root of a number, I mean this, which I think you'll all be familiar with. So the square root of 4 is 2, and the square root of 9 is 3, and the square root of -1, may or may not exist to you, depending on what you've studied in the past. Okay, so I'm going to open a poll. I just want to try this. I'm going to ask you if you understand this vocabulary. So for each new phrase or word that we have introduced, I want you to click to tell me whether you think you understand it. Did you already know it? Did you not know it, but now you understand it? And if you still don't understand it. Okay, so don't answer in the chat, but answer in the poll. Okay, this is looking good. Quite a few of you have learned some new vocabulary already, so that's really good. Some of you know that the square root of -1 is I. Okay, we won't need that today. Okay. So almost everybody has now voted, and you all seem really confident with this vocabulary. So I think we're ready to move on. Okay, Ihor, no, we're not going to use complex numbers today. Right, so you all have different backgrounds, and I'm not sure what your background level of mathematics is. So I'm quickly going to do a demonstration of expanding. Okay, so I'm just going to expand these two brackets. If you've seen this before, don't worry, it won't take us very long. Okay, so when we expand brackets, what we mean is we need to distribute all of the terms. So we have 2 root 5 times root 5y. So that's 2 root 5 times root 5y. Okay, plus 2 root 5y. And then minus 3y squared times root 5y, and then minus 3y squared times y. Okay, and then we want to simplify this as much as possible. Root 5 times root 5 is 5, and 2 times 5 is 10, so that's 10y. 2 root 5y, there's nothing we can do with that, so it's plus 2 root 5y. 3y squared times root 5y, so that's going to be minus 3 root 5. Y squared times y is y cubed, and 3y squared times y, that's minus 3y cubed. And then we can simplify this a little bit. So from the first two terms, we can take out a 2y. So that's going to be 5 plus root 5. And from the next two terms, we can take out 3y cubed. So that's minus 3y cubed and root 5 minus 1, like that. So this is what I mean when I say expanding. And most of the algebra that we're going to need today is encapsulated in this example. So Pell equations don't require very much special algebra, but it's a pretty interesting equation to be able to solve. Okay, somebody's asked, what level of maths do I have to know for understanding this? Pretty much, if you can understand what I've just done here, you're going to be just fine. And somebody said, isn't it root 5 plus 1? Yes, it is root 5 plus 1. Two root 5, 2 root 5, root 5 plus 1. Yes. Here, because I've got the minus here. Yeah, and we need both of those to be negative. Exactly. Okay. Next, we are going to need a little bit of factorizing. So we're just going to run through how to factorize these expressions here. So we're looking for what is common in both of the terms. So for the first one, we can take out a 4x, and from the second one, we can also take out a 4x. So we can write that as 4x. And what do I need to get 12x back? Is going to be 12x squared, would be 3x. And to get 20x back, I would need a -5. So like that. So if you expand that out again, you get 12x squared minus 20x. Okay. This next one here, you might recognize as the difference of two squares. And this is an important thing to be able to factorize. This would be a minus b times a plus b, like that. Okay. And if you expand that out again, you can just check that you definitely do get a squared minus b squared. So a times a is a squared plus ab minus ab, and then minus b squared, and the plus ab and minus ab cancel. So this really does work, and that is called the difference of two squares. Last one, we're going to combine these two techniques. So we can take out a y from each of these terms. So that's 16y squared minus 9. And 16y squared and 9 are both squares. So we can write that as y, that's 4y all squared minus 3 squared. And we can apply the difference of two squares technique. So that's y, 4y minus 3 and 4y plus 3, like that. Okay, so those are the factorizing techniques we're going to need. So between the previous example and the ones that we've just done, that's pretty much all the algebra we're going to need. Okay, so on to my first question, and I want you to fill up the chat with your answers. Can you find any pair of integers, x, y, that solve the following equation? And they do need to be integers, okay? And the equation I'm going to show to you now. X squared minus 2y squared equals 1. Okay, so I want you to give me your answers in the form x, y, like that as a pair. 1 and 0, absolutely. 1 and 0. I'm glad somebody said that. This is called the trivial solution. And Ilya is the first person to say 3 and 2. That is the solution where x, y numbers are as small as possible, and that is called the fundamental solution. So 3, 2 is in some ways the most important. Yes, Dennis and Igor, you both got it as well. Nicholas has found another one, 17 and 12. 17 and 12. Okay, there's no special name for 17 and 12, but it is definitely a solution. You can check if you have a calculator that 17 squared minus 2 times 12 squared is 1. And Ihor, x and y have to be integers, so we can't allow square root 2. Okay, so we're not allowing non-integer solutions. Okay, so you guys have found 3 solutions. The trivial solution, we're going to completely ignore because it's so easy to see. In fact, it will always be a solution to the equations that we're going to look at. The fundamental solution, we're going to have to guess every time. Okay, so there is a way of finding the fundamental solution, but it's far too complicated for us to look at during this webinar, and it involves continued fractions. And the next solution, 1712, we're interested in how to use the fundamental solution in order to get the next solution. And the question you might want to ask is, are there more? And if there are more, how many more? Is there a limit to how many solutions there are, or can we keep on making more and more solutions? Okay, so yes, EC says we can make more. Alexander thinks there are infinitely many. When n is a natural number, and when we are looking for integer solutions, x squared minus n y squared equals 1 is called a Pell equation. Okay, and the one that we just looked at, n was 2. All right, but this type of equation, this is what's called a Pell equation. And we're going to look at how to find more and more solutions to these types of equations. And when you look at it, it looks like a very simple equation. But trying to find solutions which are bigger than the fundamental solution is actually really hard if you don't have a method. So let's have a look at a method to see how we can do that. We're going to find all the solutions for x squared minus 2y squared equals 1. And to begin with, we're going to write our fundamental solution. That's x1 equals 3 and y1 equals 2. And that definitely works because 3 squared is 9 and 2 times 2 squared is 8. 9 minus 8 is 1. All right. To find the next solution, the 17 and 12, EC fundamental solution means it's the smallest solution, which is not the trivial solution. So fundamental means where the x and y number are as close to 0 as possible without actually being equal to 0. And the word fundamental means like the most important. Okay, or the foundation, the basis of all the other solutions. To find the next one, we're going to look at our Pell equation and apply difference of two squares. We could factorize it like this. Okay, and if we expanded those brackets, we would get the Pell equation back. And if we have a look at this bracket here, when x is x1, that's 3, we get 3. And when y is y1, that's 2, we get plus 2 root 2. So that second bracket there becomes x1 plus root 2 y1. So that's 3 plus 2 root 2. If we square that bracket, we get 3 plus 2 root 2 times 3 plus 2 root 2. And we can expand this out. So we get 3 times 3, which is 9, plus 3 times 2 root 2, which is 6 root 2. 2 root 2 times 3, which is again 6 root 2. And finally 2 root 2 times 2 root 2, which is 4 times 2, so that's 8. And we can bring that together as simply as possible. 9 plus 8 is 17, and 6 root 2 plus 6 root 2 is 12 root 2. And there, I think you can see the other solution that we got. That's the 17, and that's the 12. Okay, so the next solution, I'll call it x2 and y2. Okay, we already had that solution on a previous slide. It was this one here. Okay, so we have found our next solution, 17 and 12. And you can check 17 squared minus 2 times 12 squared really does equal to 1. It's 289 minus 288. So that is indeed a solution. I want somebody to have a guess. How do you think we're going to find the third solution? Do you think you could type something into the chat to tell us how to find the third solution? Alexander says same way. So we do 17 plus 12 root 2 square. Square the bracket again using a graph. Put in 17 and 12. Nicholas is actually telling us the next solution graphically. So some of you are saying do it again. And what exactly do you mean by that? I think maybe you're thinking to put 17 plus 12 root 2 and then square that. But we're going to actually miss a solution. What we actually need to do is to take the fundamental solution. That's 3 plus 2 root 2. And instead of squaring it, we're going to cube it. And this should get us a third solution. But I want to be sure, so we'll open it up and we will check that we definitely get a solution this way. Okay, this is 3 plus 2 root 2 squared times by 3 plus 2 root 2. So this is just making the algebra a bit easier. 3 plus 2 root 2 squared, we've already done that here. And we know that works out to be 17 plus 12 root 2. So 17 plus 12 root 2 times 3 plus 2 root 2. And we need to open up this bracket here. Okay, so we get 17 times 3. And then we get 17 times 2 root 2. And then we get 12 root 2 times 3. So that's 3 times 12 root 2. And then we get 12 root 2 times 2 root 2. Okay, and I'm not going to attempt to do all of that arithmetically in my head. I'm just going to open up my big calculator in the sky and ask that to work it out for me. So 17 times 3 plus 17 times 2 times root 2 plus 3 times 12 root 2. I'm too lazy for this. Plus 12 times square root of 2 times 2 times root 2. Okay, and that tells me 99 plus 58 root 2. And we're getting 99 and 70, so what have I done? I feel like I've written something wrongly into my calculator. 17 times 2, 3 times 12. I wrote 2 times 12, it's 3 times 12. Yeah, 70 is absolutely correct. That's a 70. And so this and this, those are our next solution. So x3 is 99 and y3 is 70. Okay, and we should check. When x is 99, we get 99 squared minus 2 times y is 70. So that's 70 squared. (99 squared) is 9,801. And 2 times 70 squared is 9,800. We get 1. So that definitely is a solution. Okay, I'm going to leave it to you now. If you have a calculator, definitely use it. See if you can possibly find the fourth solution. So x4 and y4. You will need to do 3 plus 2 root 2 to the power 4. Okay, and the best way to do that is it's 3 plus 2 root 2 cubed times 3 plus 2 root 2. And we've already got 3 plus 2 root 2 cubed here. Yeah, we worked it out when we were getting x3 and y3. So if you expand 99 plus 70 root 2 with 3 plus 2 root 2, you should get x4 and y4. Okay, some of you seem all ready to have done it. That's great. I'm going to give a minute for a few more of you to have a go at that and see if you can get the answers. Do we get square root 2 because n equals 2? Ilya, yes. In general, we get square root n. Okay, so quite a lot of us are saying 577 and 408. So that's 577 plus 408 root 2. So our solution, our fourth solution is x equals 577, y equals 408. Okay. Okay, I'm going to pass it over to you guys again. I'm going to give you about 4 or 5 minutes. I want to see if you can get some solutions for x squared minus 3y squared. Okay. That factorizes as x minus root 3y times x plus root 3y equals 1. So you need to guess a fundamental solution. See if you can find small numbers, x and y, that work in this equation, but not the trivial solution. And then to find the next one, you're going to do x naught plus root 3 y naught squared. Okay, Alexandra is saying 1, 0. 2, 1 is definitely the fundamental solution. You're right. Yeah. So x naught is 2, y naught is 1. Okay, some of you looks like you found a second solution, but I'll give some time so that you can have a go. And a third solution, and a fourth. Really interesting. Yes, Dennis, very good. Ivan, we can use the brackets with the negative inside as well. We would get the same answers, except we would have to worry about making sure we do negative times a negative carefully. So it does just produce the exact same answers if we do the negative bracket. And somebody's asking, why does this work? I'm going to show you in a couple of slides. We're going to see why does this definitely work. 7 and 4, yeah. So 2 plus root 3, if you square it all, you get 7 plus 4 root 3. So the next solution is 7 and 4. And you can check that, 7 squared minus 3 times 4 squared. That's 49 minus 48, which is 1. That definitely works. Okay, and the next solution would be 2 plus root 3 cubed, which will be 7 plus 4 root 3 times 2 plus root 3. Okay, and let's have a look, see what some of us think that is. 26 and 15. Okay, so we think 26 and 15 are the next solution. Let's check that. 26 squared minus 3 times 15 squared. Let's see what those numbers are exactly. 676. And 3 times 15 squared. Fingers crossed. Definitely 675. Okay. All right, so we have seen how to solve a basic Pell equation. We guess the solution, and then we make this bracket x naught plus root n y naught, and square it and cube it and take it to the power 4 and we keep on making more and more solutions. We have about half an hour left, so I'm going to show you a couple of problems where we can use Pell equations, where we might not expect to be able to use Pell equations. Alamhan, yes, we can do this infinitely. And if we have time at the end, I will show you a proof that we can do this infinitely and it will always work. Okay. But let's suppose we're given this equation here and we want to find integer solutions in x and y. It doesn't look like a Pell equation. X squared plus 3 is 20y squared plus 4x. But we're going to see if we can coerce it, if we can rearrange it so that it looks like a Pell equation. Okay, so let's get the 3 on the right-hand side and all of the variables onto the left-hand side. So we have x squared minus 4x minus 20y squared equals -3. And we've got 3 terms on the left. We only really want to have 2 terms. So I'm going to do a technique called completing the square, which you might not have studied yet, but that's okay. For x squared minus 4, we can write that as x minus 2 all squared and minus 4. Okay, and then the 20y squared we'll just leave for a minute. And that 4, we're going to move it onto the right side. So we get x minus 2 squared minus 20y squared equals -3 plus 4 is 1. So this is a Pell equation, right? It's of the form something squared minus an integer times something squared equals 1. This minus 20y squared, though, 20 is a big number, and it's hard to see a fundamental solution for this problem. So instead of 20, what we can do is we can be a little bit sneaky. I'm going to write that 20 is 5 times 4, and then put the 2 inside with the y. So x minus 2 squared minus 5 times 2y squared equals 1. This is even better because now n has become 5, and it's much easier to see what is the fundamental solution. So I'm going to let big X be x minus 2, and big Y can be 2y, and we get x squared minus 5y squared equals 1. Okay, and that looks much easier for us to solve. So I wonder if somebody can guess the fundamental solution for this one. Let's see if we can get x0 and y0. The numbers are a little bit bigger. Put in the chat if you think you can find x0 and y0. We have 11 and 4, 9 and 4, 1 and 0. Eleonora, 1 and 0 definitely is a solution, but it's the trivial one, so we ignore that. A couple of you have said 9 and 4. So if x0 is 9 and y0 is 4, does that definitely work? So that would be 9 squared minus 5 times 4 squared. So that's 81 minus 5 times 16, which is indeed 80. Yes. And you can check that there are none smaller than 9 and 4. So 9, 4 really is our fundamental solution. Okay. And because we're dealing with big X and big Y, when x0 is 9, that means that little x minus 2 is 9. So our first solution for little x for this actual problem is 11. And when big y0 is 4. Big Y is 2 times little y. So that's 2 times little y naught is 4, which means that y naught is 2. Okay, so 11 and 2 should solve this equation. And in fact, you can check that they do. And if you want to make more, solutions, we need to go back to the 9 and the 4, and we would do 9 plus root 5 times 4 and square it. And that would get big X1 for us, and it would also get big Y1 for us. And we could use that to find little x and little y. Ivan, this line here, you've just asked about this line here. That one there. The square is affecting both the 2 here and the y. So 5 times 2y squared is 5 times 2 squared times y squared. So that's 5 times 4 times y, which is 20y. Okay, this is great. So some of you guys got x1 is 163 and y1 is 36. So that should also solve this equation at the top there. And you can check that by putting them in. Yeah, that's right. Yeah, so x1 would have been 161 and y1 would have been 72. Sorry, that should be big Y. Yeah, exactly. Yeah, you have to convert back to little x and little y. Okay, so we have learned a bit about how to solve some equations that don't look like Pell equations, but can be turned into Pell equations somehow. Okay, it's 10 past 10. So what I would like to do is I'm going to prove to you that this process will keep on working forever. And then I'm going to pose a couple of challenges for you. And I'm going to give you an email address that you can email your solutions to. And I'll let you know if it was correct or not. Okay. So let's quickly see a proof that this will always work. Let's switch to a nicer color. Let's go with black. Okay. Proof. And what we're going to do is suppose that x1, y1 is the fundamental solution of x squared minus n y squared equals 1. And suppose that xn, yn is another solution. Okay, so suppose xn, yn is another solution. Okay, this is what we've been doing in the previous few examples together. And we're going to prove that when we take x1 plus root n y1 and times with xn plus root n yn, oh, I shouldn't use n. This is terrible notation. This needs to be a k. I've already used n for something else. Yes, that should be a k. And to make new solutions, what we've been doing is we've been taking x1 plus root n y1 and multiplying with xn plus root, I keep wanting to write n, root n yk, like that. And we expand this out and we look at the bit with a root n and the bit without a root n to get the next solutions. So let's expand out. We get x1 times xk, and we get root n y1 times root n yk. So that's n y1 yk. We get root n y1 times xk, and we get root n yk times x1. Okay. So we've expanded out, and we've been saying that this one here is xk plus 1, and that this one here is yk plus 1. And we need to make sure that xk plus 1 and yk plus 1 both solve the Pell equation at the top. Okay, so we just need to make sure that x1 xk plus n y1 yk squared minus n times y1 xk plus yk x1 squared is definitely equal to 1. All right, we shouldn't be scared of the algebra. We should be able to do this. We're going to get quite a few terms, but that's fine. This will become x1 squared xk squared plus n squared y1 squared yk squared plus 2 lots of n times x1 xk y1 yk. Okay, and minus n times, and we need to open up the other bracket there. And that will be y1 squared xk squared plus yk squared x1 squared plus 2 lots of y1 xk yk x1. Now, this 2n x1 xk y1 yk, because we have a minus here, n times 2 y1 xk yk x1, that's going to cancel. So all we've got left is x1 squared xk squared plus n squared y1 squared yk squared minus n y1 squared xk squared minus n yk squared x1 squared. So it's gradually getting better. It still looks pretty ugly, but let's try and factorize if we possibly can. Hijo, that's a really good question. Are we going to lose any answers using this method? I'll address that in a moment. Let's finish off this algebra. This term and this term both have an xk squared. So that will be xk squared times x1 squared minus n y1 squared. Factorizing. This term and this term both have a yk squared. So we're going to say that that is minus yk squared. Or we can take out an n as well, actually. Yeah, that will be x1 squared minus n y1 squared. Okay, x1 and y1 are solutions of the Pell equation. And look, this is the Pell equation, and this is the Pell equation. So both of those square brackets have to be 1. So we've got xk squared times 1 minus n yk squared times 1. But look, xk and yk are also solutions of the Pell equation by assumption up here. And that is the Pell equation. So that must equal to 1. So to summarize, what we did was we took xk plus 1 and yk plus 1, we put them into the Pell equation, and we got 1 at the end, which means that xk plus 1 and yk plus 1 are definitely solutions of the Pell equation. Okay, so that proves that the answers we're getting will always be answers, and we could keep on doing this forever without stopping, and we would keep getting solutions. Now, Iho's question, do we ever lose solutions? So although we get infinitely many this way, are there some that we don't get this way? The answer is no. This gives all solutions. None are missed. But this is hard to prove. Okay, And if you would really like to see this type of question, this type of proof, then you could Google Pell equations, and there's a lot of articles online about that. Xiang, this is indeed induction. Yes, so this would be an induction proof. I don't think you need to understand induction to know this works, but this actually is mathematical induction, yes. And from EC, do these questions come up in A-levels? No, they do not. You might see them in competitions. If you're going to be a researcher one day, you might see these problems coming up in research sometimes as well. I have some computer scientist friends who once sent me an email because they had a Pell equation. They'd never seen one before, and they needed my help to solve it. And Svetlana, this workshop finishes at 10:30, so we have only about 10 minutes left or something. And Dariga, how is this method called? It's not really got a name. It's just a way of solving Pell equations, and there are other ways. Ilya, yes. This method of proof here is called mathematical induction, but the method we're using to find the solutions doesn't really have a name. It's just an algorithm. Okay, right then. So here is my challenge to you. I won't talk about the solution, but if you can work out your solution, I'll leave an email with you at the end, and you can tell me if you think you have solved it. You have n dots. For which values of n can you arrange the dots into a square and a triangle? Now, the type of triangle I'm talking about, it has to look like the one I've drawn. Okay, so this is a 6 by 6 square. So n equals 36 is one solution to this problem, because it's equal to 6 times 6. And if we arrange it into a triangle like this, we get 1 plus 2 plus 3 plus 4 plus 8. Okay, and that is also equal to 36. So you're trying to look for numbers where it's possible to do this, put them into a square, and to put them into a triangle like that. Ilya has said m squared and k times k plus 1 over 2. Yes, so Ilya's way of interpreting this problem is definitely a good starting point, but I'm not going to tell you any solutions. So that's your problem, that's your homework. In the chat, I'm going to put in my email address, so please feel free to email your solution to me, and I will tell you if it's right or wrong. EC says, will there be more classes like this? EC, the answer is yes, and the more people come to them, the more we will do. And I'm going to tell you, actually, we have one of these webinars for chemistry turning up. And I'm going to tell you the details of that just now. So we have one on the 8th of April. So that's in a week from today at 9:30. Okay, so on the 8th of April at 9:30, there is a chemistry in your home webinar. Chemistry in the home. So we're looking at all kinds of experiments that you can do at home using chemicals that you can find around in the cupboards. And that is most suitable for 14 to 17-year-olds. It will also be on Zoom. Okay, so if we've got your email address, keep an eye on your emails. Ilya, what about math webinars? Yes, I will definitely do this again. This is my first ever webinar. It's been a fantastic experience. From Penny, who is running the chemistry? That will be Dr. Robotham, and she is the head of science at the National Mathematics and Science College. So chemistry will be with Dr. Rowe. EC, what's happening with year 13 results this year? How are they getting students to uni with bad predictions? It really depends on your school or college, whoever you're with. So you really should speak to them in the first instance. The exam boards are communicating with the schools about how to calculate the grades. So your school should be able to tell you exactly how they're going to calculate that. It is challenging, but by and large, teacher predictions tend to be really reliable. So I don't think you have anything to worry about too much. The other thing is, EC, you will be able to do some exams, I think, in September. If you're not happy with the grade that you were given, there'll be an opportunity for you to do some exams. Alexandra, what will be the topic of our next webinar? It's a great question. I will have a dig around in my box of interesting maths topics to see what I can find. Maybe something to do with continued fractions could be interesting, or Pick's theorem could be an interesting one for us to look at. EC, I wouldn't worry. I don't think you have to worry too much. The students who are getting good predictions, or there's not going to be any lucky students or anything like that. Yeah, the exam boards are going to do everything they can to make sure it's as fair as possible. But that's really good, Alaman. I'm very glad to hear that. You can watch the video back. So I'm going to send you an email with a link where you can watch the video. So you'll be able to see all of the different techniques that we did, and you can pause it and have a think about each equation if you like. And thank you, Jane. Yeah, you can follow us on Instagram, natmatsci, and natmatsci on Facebook. Okay, and we'll post the dates there. But we also do have your email address. So we'll put you on a mailing list and make sure you stay informed. Okay. By the way, this is the next solution for that triangle and square problem. I don't think counting the dots is going to be a very good way to do it. There are lots and lots there. Okay, so that's the next solution. And there will be another one after that and another one after that as well. The triangle, it does have to have the same height and width. Yes, it does. So it's got to be in the same form as this one. So this is an isosceles triangle. It's 8 by 8, just like that. Okay. Right, I think I'm going to call it a day. Make sure to email me your solutions, and I hope to see you at our next webinar, which is on the 8th of April at the same time, and it's all about chemistry in your home. And I'll let you know about more upcoming math webinars. EC, very quickly before I go, for the number of dots in a triangle, it's going to be 1 plus 2 plus 3 plus blah, 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 plus, let's suppose this A, let's call that B. So plus B. And you want to know the formula for this. Okay. If you write this again backwards, you get B plus B minus 1. So we're writing the same thing again and backwards, B minus 1 plus B minus 2 plus da da da. And at the bottom will be 1. That's also equal to S. It's just written the other way around. If you take the sum, so B plus 1 is B plus 1. B minus 1 plus 2 is also B plus 1. B minus 2 plus 3 is also B plus 1. And you'll have more. And then the last one, B plus 1, is also B plus 1. And that must be 2S. how many b plus 1s are there? Well, there are b many. So this is b times b plus 1 is 2s. So s is b times b plus 1 divided by 2. If you apply that formula to this triangle here, that's 8 times 9, b times b plus 1, and divide by 2. It's 9 times 4, which is also 36. Okay. All right, guys, I really have to go. It was lovely meeting you all, and I hope to see you next time. Have a great evening, morning, afternoon, wherever you are. Ilya, can n be negative? You want to Google, Ilya, Pell type equations. Okay, that's an extension to Pell equations, where you can have different things on the right-hand side and different types of values of n. So Pell type equations. Okay, bye-bye, guys.